So now that I have all three servos in their 0-degree position, I can go ahead and build an articulated manipulator. When we draw the kinematic diagram of an articulated manipulator, which, if you will recall, looks like this, we are making the assumption that in this position, as shown in our diagram, all of the servos are in their 0-degree position. So when I build my articulated manipulator, I want to build it so that it looks like this. It's in this position with all of the servos at 0 degrees as they are right now. So the first thing I'm going to do is attach my servo 1 to the board. Now I have to make sure that I put these servos in the right order. The next one I want is the servo that's connected to pin 3-1. This one's connected to pin 3-4, so that's my third servo. This one is connected to pin 3-1, so it's my second servo. I need to attach it like this, and I need to make sure that the horns are lined up so that the axis of rotation of this servo will intersect with the axis of rotation of this servo. With two of these little screws, which are 256 screws, the numbers on screws refer to the diameter of this screw and also the threads per inch. So I'm then going to attach this one like that. Okay, now in order to make this match my kinematic diagram and the position it's in, I need to connect the next servo like this with a straight link in between them. Now I'm going to look at this from a little bit of a different point of view in order to show you how we have to hook this up. Here's a side view of what we're doing. Now you can kind of see from this first servo horn that I'm not going to be able to use a straight link to connect these directly together. The holes won't line up. When I attach a straight bracket here, it's going to be angled like that in order for the holes, are the holes lining up here? In order for these holes to line up. Or I could rotate it 90 degrees and have the holes line up again and attach it like that. But I really want this to be just like that at 0 degrees. There are a couple of different ways that we can solve this. One way would be to unscrew this screw in the center, rotate the horn so that it lines up, and then press it back on. I'm going to show you how to do that solution here. Here's how you use the first solution to get these things lined up just like our kinematic diagram. I'll take my screwdriver. Now note that this servo is still holding its position at 0 degrees. I'm going to remove the screw in the center and I'm going to pop off the servo horn just by pulling it. If you look closely at this servo horn, you'll see that there are gear teeth cut into the horn, and there are also gear teeth here at the top of the servo. So what I'm going to do is I'm going to press this up against here, and as I rotate it around, you'll feel the two gear teeth catch. And I'm going to press it back on in such a way that the holes here line up nice and straight. So then I'll just press the horn back on carefully with my hand, and then I'll screw this screw back in. When I tighten this screw in the center, it will effectively press the servo horn on much tighter than I can just press it with my hand. So I'll tighten up this screw. Now the servo horn is nice and aligned. I'm now going to attach this straight bracket to the servo horn with 2 of these 256 screws, and then I'll tighten them down. There we go. Now our first 2 servos match the orientation shown in our kinematic diagram. The first link goes straight up, and the second link comes straight out at a 90-degree angle. So it's the same in my physical manipulator as it is in my kinematic diagram. Now I need to do the same thing with my third servo. Right now, if I would attach this third servo like this, when I line up the holes, I can either attach it like this so that the holes align, or I could rotate it 90 degrees and attach it like this. But I really want to attach it very straight, just like this. So I'm going to make the same change to this one. I'm going to start by unscrewing this center screw. I'm going to pop off the servo horn. You just pull, it'll come. And then I'm going to line it up, rotate it just lightly so that I can feel the gear teeth catch with each other, and line it up so it's nice and straight. And then I'll press it on with my hand. So you can see that now I've got it so that these 4 holes are very straight. I'll put the screw back in the center, and tightening this screw down will attach the servo horn more securely. Now my actual manipulator is in an orientation that matches my kinematic diagram when the angle of 0 is set to each of these servos. Now it's not perfectly exact. You can see that my third servo is angled up a little bit, but it's pretty close, and it's going to be close enough for our purposes. Now that we have our manipulator built, I'd like us to be able to move it around and reposition the end effector. Since we haven't yet learned how to command the end effector to move to a position, let's hook up some buttons that we'll be able to use to move the end effector around. Start by taking 4 buttons and plugging them into your solderless breadboard. So I have one button here, and I see it's off the screen. I'm just going to slide. There we go. If we hook up 4 buttons, we could use one of these buttons to determine the direction that a servo will move, and we can use the other 3 buttons to move each of the 3 servos in our manipulator. Once you've hooked up these 4 buttons, make sure that the buttons are not touching each other so you don't have any shorts in the wires. There we go. Now, one end of each button needs to be connected to power. So I'm going to use a jumper wire to connect one of the leads of each button to power. And I'm connecting it to my power rail. Now, the other lead of each button needs to be connected to an input pin. I'm going to use for my input pins 20, 21, 22, and 23. Those pins, if we flip the PSOC over, those pins are along this end here. This is 20 right there, 21, 22, and 23. So if I use those 4 pins, they'll be all right next to each other. So I'm going to connect the other lead of one of these buttons to pin 20. I'll connect the other lead of button 2 to pin 21. I'll connect the second lead of the third button to pin 22. And I'll connect the other lead of the fourth button to pin 2, 3. Okay, once we've got this wired up, let's go write some code. I have open here the code that we ended with last time when we were setting all 3 of our servos to the 0 degree position. Go back to your top design, and we're going to place some pins to read the switches, or the buttons that we just wired up to our PSOC. Find the Ports and Pins menu and find the digital input pin. Drag 4 of these to your screen. Now we already have 3 pins wired to the PWMs, and now we have 4 pins to be used as buttons. This can start to get confusing to remember which number of which pin refers to what. Let's rename these pins. Double click on the pin and let's change its name to switch 1. Also, under drive mode, instead of high impedance digital, select resistive pull down. What this means is when our button is not pressed, this pin will be automatically connected to ground. If we don't select resistive pull down here, the pin, when it is not connected or when the button is not pressed, the pin will not be connected to ground. It will not be connected to anything, and that will make it behave in a strange way. So make sure you choose resistive pull down in the drive mode. For the next pin, let's change its name to switch 2. And also select resistive pull down. The next pin, we'll name it switch 3, resistive pull down. Change this one to switch 4 and select resistive pull down. Next, go to the CYDWR window and set switch 1 to pin 20, which is the pin that we used to plug in our first button, 21 for switch 2, 22 for switch 3, and 23 for switch 4. Now let's write some code. Go to your main.c window. Now we're going to use switch 1 to determine which direction the servo will turn, and then we'll use the other buttons to make each of the different servos turn. So let's do this. First, under int tix3, let's create a new variable called direction, and let's let this be a float. Now, inside the for loop, let's read the value of switch 1. This if statement says that if switch 1 is high, that is, if switch 1 is pressed, then we'll do the things that are inside of these two curly brackets. In our case, let's make it be that if switch 1 is high, then the value of the direction variable will be 1. Else, that is, if switch 1 is not pressed, we'll execute what's inside of these two curly brackets. In that case, let's make the value of direction be -1. Now, here's how we can use that direction variable. Let's put in another if statement that checks the value of switch 2. If switch 2 is pressed, the code will execute everything inside of these two curly brackets. If switch 2 is pressed, let's make the value of angle 1 be equal to whatever it's currently equal to plus the value of direction. What this means is if switch 2 is pressed, angle 1 will either be equal to angle 1 plus 1 or angle 1 plus -1. In other words, if we have switch 1 pressed and we have switch 2 pressed, then angle 1 will become larger every time through this loop. If we have switch 1 not pressed and we do have switch 2 pressed, then angle 1 will become smaller every time through this loop. In this way, we can use two buttons, switch 1 and switch 2, to make servo 1 move in both directions. Let's do the same thing with the other angles and the other switches. If switch 3 is pressed, let's make angle 2 be equal to angle 2 plus direction. And finally, if switch 4 is pressed, we'll make angle 3 be equal to angle 3 plus direction. Lastly, since we're now able to change the values of the angles, let's make sure that the angle never becomes outside of the range that it's supposed to. So let's do this. If angle 1 is greater than 180, then we will make angle 1 equal to 180. This will prevent us from accidentally driving servo 1 beyond its maximum 180-degree angle. We should also prevent angle 1 from being driven below its minimum 0-degree angle. So let's say that if angle 1 is less than 0, we will set angle 1 to be equal to 0. This way, if we try to drive servo 1 below 0 or above 180 by pressing our buttons, our code will not allow the servo to try to move beyond its limit. We can also do this for the other two angles. If angle 2 is greater than 90, then angle 2 should be equal to 90. Remember that servos 2 and 3 are limited to the angles 90 and -90 instead of 180 and 0 like the first one. So if angle 2 is less than -90, we will set angle 2 to be equal to -90. We'll do the same thing with angle 3. Okay, let's build this code and check to see if we have any errors. If the build succeeded, go ahead and program the PSOC. Let's take a look at how this works. We know that one of our buttons will do nothing because it's the direction button. We also know that another button will do nothing initially because it's trying to move servo 1 in the negative direction, and servo 1 is already at the 0 position, so it won't be able to move. The other two buttons should move the servos 2 and 3. Let's try pressing the first button. Nothing happened, so this is probably our direction button. Let's try pressing the next button. Nothing happened there either. This one is probably servo 1. Let's test this by pressing both buttons. If I press the direction button at the same time as the servo 1 button, servo 1 should try to move in the positive direction. It does. Now, let's try to move servo 1 in the negative direction. Servo 1 will move in the negative direction when we are not pressing the direction button and we do press the servo 1 button. Here's servo 1 moving in the negative direction. Let's try our other buttons. This next button will probably move servo 2, and since I'm not pressing the direction button, it will move in the negative direction. This one is moving servo 3. Let's try and move servo 3 in the other direction. Let's try the last button. This one is moving servo 2 in the negative direction. If I press the direction button at the same time, servo 2 should move in the positive direction. The way we've set it up in the code is that each servo will move in the positive direction when the direction button is pressed, and it'll move in the negative direction if the direction button is not pressed. Do some testing right now to determine which direction is positive for each of your servos. For example, I'm going to hold down the direction button and press the servo 1 move button. It moves in the positive direction. This shows me that the Z direction for servo 1 is up, because when I move it in the positive direction, it moves in the same direction that my fingers are curling. Next, I'll hold down the direction button. Well, first I'll move it back to its original position so that you can see from the side. Now I'm going to hold the direction button and move servo 2. This is the positive direction for servo 2. This means that the Z-axis should be pointing in the direction shown by my thumb, because this is the direction the servo is moving, in the positive direction. Let's move it back down. Now I'm going to hold the direction button and move servo 3. This is the positive direction for servo 3. This means that the Z direction should be in the direction shown by my thumb, because the link, which is here, moves down when I move it in the positive direction. Now notice that it will be possible for me to drive this manipulator around in such a way that we make the end effector hit the table. We would like to avoid this happening. We can use our forward kinematics knowledge to write some additional code to prevent a person driving the manipulator from being able to smash the end effector into the table. And I'm now going to show you how to do that.